Welcome to the Electrical Power Explained webinar. This webinar will start with a simple DC circuit connected to a pure resistive load. But soon, AC power will be introduced, and theory needed to calculate powers correctly will be explained. With the introduction of AC power, we will also take the phenomena of harmonics into account. Once we understood these single-phase basics, we start to discuss the AC power in three-phase systems. First, we will build up theory in an ideal world, in this case meaning a three-phase system perfectly balanced and without the presence of harmonics. But in our daily practice, the power systems are not perfectly balanced, and nowadays more and more harmonics are present with a negative impact on our machines, transformers, and systems. Here, we will also see that classical power calculations do not fulfill anymore, and enhanced calculation methods like unified power and IEEE 1459 will be discussed. Unified power method supports the concept of current decomposition, and this makes the useless currents in the system visible. The losses of these currents can be calculated and focused countermeasures can be taken. The objective of this webinar is to give all the theory needed to fully understand the sources of line losses in electrical systems. This webinar consists of 6 modules, and each module will be finalized with a quiz. This slide shows the webinar overview with all subjects we will discuss. The webinar consists of 6 parts. Part 1 will discuss the basics of both DC and single-phase power, and also harmonics will be introduced. Part 2 presents the basics of three-phase systems, and the difference between Y and delta systems will be explained. In Part 3, we will see what is meant by unbalanced three-phase systems and how we can calculate the powers in these systems. We will see there are different methods, each giving different results. Part 4 will discuss the combination of unbalance and harmonics, which result in neutral currents. Power losses are explained in Part 5, with a focus on the Joule effect or losses by heat. We will also have a look at the energy loss calculator that gives insight what currents bring on these losses. Part 6 will give a summary of the theory that was explained in the previous parts. Electrical Power Explained, Part 1. In this part, we discuss DC power and single-phase AC power. We will go over power in resistive loads, inductive loads, and we will introduce distortion by harmonics. Basic DC power. Basic DC power. We start with DC power for, say, a simple flashlight. DC is important to a power engineer because it includes the outputs of switch-mode power supplies that are found in many types of electronic equipment. DC is also still used in automotive and locomotive transport and some motors. And since the outputs of solar panels are DC, it is making something of a resurgence in importance. Part of the work is to define the symbols used in IEEE 1459 and elsewhere. Things get complex further on, so to understand exactly what is going on, it's important to get the basics right. The diagram shows a 6-volt battery driving 1 amp into a 6-watt incandescent lamp. Ohm's law. The basic equation governing voltage and current was first published in 1827 in a book written by George Ohm. The simple statement of U equals I times R, or voltage equals current times resistance, started the whole subject of power metrology. Power. DC power is represented by a capital P and measured in watt. When we need to be clear, we use subscripts to confirm that values are DC, but leave them off when it's obvious what is referred to. Energy. Power is the rate of energy flow in a circuit. So, energy is the power multiplied by the time T that it flows, generally measured in watt-hours or kilowatt-hours. If the power is not constant, you can approximate it by taking many samples, each lasting a short time, delta T, over which the power delta P is near constant. Then, the energy is the sum of all the individual power samples. Single-phase power with resistive loads. Resistive loads, basic AC power. For basic AC power into a resistive load, the voltage UAC across the load pushes a current I into the resistance R. The illustration this time shows a mains voltage of 120 volt at 60 Hz driving 5 amp into a powerful 600 watt lamp. This could be a stage spotlight or a ring circuit of 30 20 watt lamps, for example. Instantaneous voltage, current, and power. With AC, the voltage, and so the current and power, vary over time. The most general statement is that instantaneous power, PT, equals UT times IT at any time. Rotating generators have traditionally generated the voltage that supplies the current. When something rotates, the height of each point on the circumference varies as a sine wave. So, a generator produces a sine wave voltage. Utilities, incidentally, are primarily interested in supplying a voltage. Users take current from the supply, but this shouldn't influence the pure sine wave voltage supply. Parameters. We want to describe a waveform without going into all the complex time-related details, so we simplify by defining parameters. These are measurable properties of varying waveforms like UT, IT, and PT. But for instantaneous values that are always changing, what do the figures 120 volt and 5 amp refer to? They are not the peak values, and they are not the average values for which sine waves would be 0. They generate an average power of 600 watt in the load, though, giving the same heating effect as would a 600 watt DC power. The voltages and currents URMS and IRMS are actually root mean square values. We will now explain why these parameters are useful. Resistive loads, RMS values, and why we use them. We can describe the value of UT using the peak value U peak and the sine wave function. The instantaneous value is now given by the peak value times the sine of the angle at any time t as it repeats at frequency f. Same for instantaneous current. Instantaneous power is, as before, PT equals UT times IT, where PT is constantly fluctuating. We now need a single figure to represent the average power that this varying voltage can deliver into a load to correspond with or develop the same heat as a DC power P. The average value of the instantaneous power PT, similarly, has parameter value P. We can't, however, find this average power by multiplying the average values of voltage and current, because the average values of a sine wave are 0. We therefore need to get rid of the negative parts of the signal, and RMS is the most useful way of doing this. Separate out the instantaneous values of the varying voltage into n instants, and the RMS value is defined by URMS equals the square root of the mean of the squares. For a pure resistive load like our lamp, voltage and current are in phase. This means the formula for power is in this case P equals URMS times IRMS. Here and elsewhere, RMS means that you don't have to worry about the time function. To find the average power in a resistive load, you simply multiply URMS by IRMS. Although the root mean square is an abstract concept, it is very useful in power calculations because P equals U divided by R. And this equals I squared times R. So the square of the values of UT and IT do represent something real, the heat loss across a resistor. Resistive loads, RMS voltages. We can look at the voltages as they could appear on an oscilloscope. The sine wave at the top repeats once every period t. Rather than showing the time in seconds, we show the phase angle of UT and again by convention, divide the cycle into 360 degrees. Squaring the instantaneous voltage prevents the negative values from simply canceling out the positive ones, and also doubles the frequency. Power is now pushed into the load once every half cycle rather than every cycle. The current flows first one way and then the other, but both times generates heat. Again, the power P equals U squared divided by R. We can find the relation between U peak and URMS by looking at the square of the sine wave. For our 120 volt RMS, the average value U squared is by definition 120 squared, and the peak to peak is 2 times 120 squared. Taking the square root confirms that URMS is 120 volt, which means that the peak value U peak is 170 volt. Once again, the 120 volt URMS is the voltage that will produce the same heat in a resistor as will a DC voltage of 120 volt. Resistive loads, RMS voltage properties. So, what are the basic properties of RMS voltages? Adding RMS values. You can only add the RMS values of two signals directly if they have the same frequency and phase. If the two signals have the same frequency but are shifted in phase, the resulting RMS value can vary from twice the RMS value of a single signal when they are exactly in phase to 0 when they are exactly shifted half a period. In general, if you want to add the RMS values of voltages with different frequencies, you have to add the squared values and then take the square root. RMS for a pure sine wave. For a pure sine wave, and only for a pure sine wave, the RMS voltage is the peak value divided by the square root of 2. Incidentally, don't confuse the RMS value URMS with U average, the rectified average value. Although the average value of an AC signal is 0, rectify it and you get U average, since full-wave rectifiers convert the negative values to positive ones to give the modulus UT. The RMS value is slightly 1.11 times higher than the average. The old analog moving coil voltmeters used to simply rectify a sine wave and multiply the average by 1.11 to show RMS. Again, this only works for a pure sine wave and otherwise gives incorrect results. So, average values are only ever of interest if you have a pure sine wave. Parameters. The two key voltage parameters for a rectified sine wave are the peak and the RMS values. Once again, you use the RMS value to find the power that voltage will develop. Resistive loads, voltage and current in phase. Multiplying the instantaneous voltage and current waveforms gives the bottom waveform, the instantaneous power PT. So, even though the averages of the RMS voltage and current are 0, the average power is positive, in itself an interesting result. RMS voltage. For the sine wave voltage UT shown, URMS is 120 volt. RMS current. Similarly, for IT, IRMS is 5 amp. Multiplying them gives average power for a resistive load. The waveform at the bottom shows the instantaneous power, PT, equals UT times IT, which is always positive. The average power P equals average PT, which is 600 watt. Inductive loads, introducing phase shift. This time, we have an inductive load like a motor. Again, IAC and UAC are in capitals to show steady values. We've chosen the same 120 volt RMS supply, pushing 5 amp into a load for easy comparison with the resistive load. The motor is labeled 120 volt 600 VA and cosine phi equals 0.866, which will be explained in the next few pages. Instantaneous values. As before, the instantaneous values are UT, IT, and PT, and the instantaneous power is PT equals UT times IT. Parameters. The magnetic field set up by the coils forming an inductive load resists any sudden change in the current, which means that a change in voltage doesn't immediately change the current. The current lags behind the voltage. That gives an extra parameter, the phase angle between voltage and current, phi UI. So, what is the value of the power now? Inductive loads, voltage, current, and power. We now again draw the voltage, top graph, current, center graph, and power, bottom graph. Voltage and current. We have the same RMS value of 120 volt as before. We again have a current of 5 amp, but this time, notice the phase shift of minus 30 degrees between voltage and current. Minus because IT lags behind VT. It reaches its first zero crossing 30 degrees after the first zero crossing of UT. For a pure inductor, the phase angle would be minus 90 degrees. So, the same amount of energy would flow back into the supply in the second half cycle as is transferred to the load in the first. Motor windings have both resistance and inductance though, which alters the phase angle. In motors, the current can typically lag the voltage by 30 degrees, so we say phi UI equals minus 30 degrees. Notice the minus sign again. So, how does this phase shift influence the power? Instantaneous and average powers. Again, we have UT, IT, and the most general statement for the power of a waveform, PT equals UT times IT. And again, we can multiply the instantaneous values of voltage, top graph, and current, central graph, using an Excel spreadsheet to give the power as it varies over time. The period is half that of UT and IT, so the frequency is 120 Hz. Twice in the cycle, when voltage is positive and current negative, and when voltage is negative and current positive, the value drops below zero, showing that power is pushed from the load back into the mains. Now, the spreadsheet will show that the average power is no longer 600 watt, but a lower figure of 520 watt. The phase shift between voltage and current reduces the average of the power waveform by 80 watt. So, for an inductive load, the average power P is not equal to URMS times IRMS. Inductive loads. Separating instantaneous into active and reactive power. But how do you calculate the exact value of average power now that it is no longer simply URMS times IRMS? A mathematical trick suggested by Charles Steinmetz back in 1879 can separate out the instantaneous power PT into two components. The first is the active power PAT. Again, a sine wave and with the same average as PT. It stays positive though and represents the power flowing into the resistive load. The second is the reactive power PRT, which we choose to go positive and negative but which is 90 degrees out of phase with the active power and has zero average power. These two form the instantaneous power at any time. The power from the supply at any instant therefore separates out into active power flowing into the resistive load plus, 90 degrees later, the reactive power flowing back and forth through the inductor. So, in the middle diagram, the active power, green, drives the motor. The remainder is the reactive power, red, which flows into the load for half the time and flows back into the mains for the other half, with an average of 0. Although the reactive power generates no torque at the axle of the motor, it still flows through the system and generates wasted heat. The bottom diagram shows the two currents associated with these powers. The active current, IAT, which is in phase with the instantaneous voltage from the utility, and the reactive current, IRT, which is 90 degrees out of phase. The instantaneous current is similarly the sum of active and reactive currents. Note that reactive power in itself does not cause loss. It is power that bounces between source and load but is not consumed. It does, however, produce reactive current, which causes losses in the system and load for the utility. Inductive loads, active, reactive, and apparent power. So what are the parameter values for these instantaneous waveforms? Parameters. Most of the time, we're not interested in instantaneous values of power, but rather the average value P, here 520 watt. The average value of active power PAT, the active power into the load, is also 520 watt. We know that the average of PRT equals 0, but this isn't a good number to represent power. We therefore represent the reactive power PRT by its maximum value. The reactive power Q equals max PRT equals 300 VA reactive. The new unit is volt-amp reactive to indicate that we are dealing with reactive power, apparent power. Seen from the utility side, URMS and IRMS are the parameters that determine the size of the network. For this reason, the apparent power S of 600 VA, the simple product of 120 volt URMS and 5 amp IRMS, is used as a measure for the power in the network. The active power is then URMS times IRMS times cosine phi. You can add active powers to each other, and you can add reactive powers to each other, but you cannot add active to reactive powers because they act at right angles to each other. The apparent power, the power that appears at the utility, is actually the vector sum of P and Q. Active and reactive currents. Now, IAT and IRT can be represented by their RMS values, IA and IR. Because we are dealing with RMS values, the apparent current I squared equals IA squared plus IR squared. We can again deduce the values. The RMS value of green, active current IA is simply 520 watt divided by 120 volt. This equals 4.33 amp. The RMS value of the red reactive current is similarly 300 VA reactive divided by 120 volt equals 2.5 amp, 90 degrees out of phase. Inductive loads, apparent power, and the canal boat metaphor. This separation of the apparent power VA into active power watt and reactive power VAR is fundamental to power quality. You can compare it to pulling a canal boat. Canal boats used to be pulled by horses walking along a towpath. The apparent power is the power developed by the horse pulling the rope. The rope makes an angle phi to the towpath, and you can separate out this apparent power into the real useful power that pulls the boat along the canal and the reactive power that the rudder has to counteract just to prevent the barge being pulled into the side. Here too, the powers are simply given by the vector sum S squared equals P squared plus Q squared. Replace the horse by a utility generator, the rope by the network, and the boat by an electric load. The utility supplies the apparent power, the real power generates real useful torque in your motors, while the reactive power goes off into the imaginary direction and is wasted. The equations. Much of what we've seen so far can be summarized in these three relationships. Apparent power, S squared equals P squared plus Q squared. Active power, P equals S times cosine phi. Reactive power, Q equals S times sinus phi. Note that you get the active power by multiplying the voltage by that part of the current that contributes to the active power, which is the cosine. So the angle phi between P and S is the same as that between U and I. You can summarize the performance of your whole system by the power factor PF. PF equals P divided by S, and PF equals cosine phi. The power factor is your primary performance indicator. It is cosine phi which gives the relation between active and apparent power. A power factor of 0 means that the current is lagging, or leading the voltage by 90 degrees, while a power factor of 1 means the current and voltage are in phase. So the smaller the angle phi, the closer is PF to 1 and the more effective your system. Inductive loads, power factor. Going back to our motor, we can see what the canal boat metaphor means for the power to the motor. We see that the inductive nature of the motor, indicated by cosine phi equals 0.866, results in only 520 watt out of the 600 watt apparent power being transported turning into active power. The remainder, 600 squared minus 520 squared equals 300 VAR, is reactive power that loads the network but does not contribute to motor torque. The efficiency of the system given by the power factor is 86.6%. The root cause of this inefficiency is the phase shift between current and voltage in non-resistive loads. Shifting the motor current closer in phase to the motor voltage by adding a capacitor to the motor circuit can improve efficiency of the system. Capacitors are usually considered to generate reactive power, and inductors to consume it. Connecting a capacitor and inductor in parallel cancels out the current. And again, apparent power S squared equals P squared plus Q squared. Electrical Power Explained, Part 1. In this part, we will introduce distortion by harmonics, single-phase power with inductive loads, and harmonic distortion. So now we look at how harmonics added to inductive loads affect P, Q, S, and power factor. The same motor is now attached to the network, but this time driven by a noisy electronic motor drive. We assume the same phase shift as before, but in addition, third harmonic current is generated by the electronics. Instantaneous values. The instantaneous values are, as before, UT, IT, and PT. Parameters. The voltage parameter is URMS again, or simply U. The current IRMS, or I, is now made up of a fundamental component I1 and the third harmonic I3. The phase angle phi1 is here between fundamental current I1 and the voltage U. There is only a fundamental voltage, so we just say voltage. Harmonic distortion simplified by Fourier analysis. Fourier's theory says that a repetitive signal can be treated as a sum of pure sine waves. Currents. Once again, we've chosen IRMS to be 5 amp. Fourier analysis can separate out the top waveform into a fundamental and a third harmonic component at 3 times the fundamental frequency. To give the total 5 amp current in the example above, the fundamental and third harmonic components calculated in XL turn out to be 4.8 amp and 1.4 amp. Here too, because they are RMS currents with a different frequency, the vector sum gives 4.8 squared plus 1.4 squared equals 5 squared. Harmonic distortion, voltage, current, and power. Multiplying the voltage and current waveforms gives the power waveform. And again, because of the motor's lagging current, we see the power dip below zero. Voltages and currents. Because the utility supply is very stable, the voltage consists of the fundamental voltage only, as we've seen before. The RMS current is the full 5 amp through the load, made up of 4.8 amp fundamental and 1.4 amp third harmonic. Powers. We can again use XL to multiply instantaneous values of voltage and current to find the average power. It turns out to be even lower, 499 watt. So we've gone from 600 to 520 to 499 watt. The apparent power that the utility supplies, however, is still 120 volt times 5 amp equals 600 volt amps, or VA. Harmonic distortion, active, reactive, and apparent power. We now repeat our previous trick, and this time we also separate out the harmonic power. So, we separate out the distorted wave of the last diagram into active, green, reactive, red, and harmonic, blue. We've already seen that the red reactive power has an average value of 0, and in this example, this is true too of the blue harmonic power. Power into the load. The power into the load is now 499 watt for the apparent power of 600 VA. Active and reactive powers. The green fundamental active power is the only wave having a net result, 499 watt. The red fundamental reactive power, Q1, is 288 VA reactive peak. Apparent powers. The utility still sees the full 600 VA apparent power S. Now though, we separate it out into the fundamental apparent power S1 and the non-fundamental apparent power Sn, which collects together all the different harmonic powers, like third and fifth harmonics. Sn is the vector difference between S and S1, equals 168 VA. The square root of 600 squared plus 576 squared equals 168 VA. Currents. Once we split out the powers, we can calculate the values of all three currents. The 5 amp now separates out into the 4.157 amp active, 2.4 amp reactive, and 1.4 amp harmonic. Because it's calculated using the vector sum, the wasted current is larger than you'd think for a relatively small difference between 5 amp and 4.157 amp. The network now sees just over 4 amp useful current out of 5 amp, with about 2.8 amp waste current, consisting of 2.4 reactive and now 1.4 amp harmonic current. That is a lot of waste. Harmonic distortion. Where does it come from? Applying a pure sine wave voltage to a linear load produces a pure sine wave current. For linear loads like heaters, incandescent lights, and motors, the value of current is simply proportional to the voltage. Linear loads do not change the shape of the current waveform, although they may change the phase relationship between voltage and current. Linear loads often refer to resistive loads, but may actually be resistive, inductive, or capacitive. Applying a sine wave voltage to a nonlinear load produces a current that contains harmonic components. The most widespread example of a nonlinear load is the rectifier circuit. This is widely used in switched-mode power supplies, variable speed motor drives, LED lights, and compact fluorescent lights, and many other electronic devices. The AC input voltage, UAC, in the single-phase bridge rectifier circuit is fed to a diode, bridge D, by a series impedance, RS. The output charges the capacitor C, which supplies the DC voltage, UDC, to R load. The voltage and current waveforms. In the top graph, the solid red line shows the instantaneous AC voltage, UT, applied to the rectifier bridge. The dotted red line shows the rectified part of UT written as modulus UT. The blue line shows the DC voltage UCT across the capacitor. Notice that this voltage is not constant, but has a ripple on it. At the left of the graph, the voltage across the capacitor is about 120 volt and decreasing because R load is discharging the capacitor. While UT is smaller than UCT, the diode bridge will not conduct because D1 is reverse biased and no current will flow. When the increasing UT equals the decreasing UCT at a phase angle of about 30 degrees, the diodes D1 and D2 become forward biased and current IT starts to flow. See also bottom graph. The value of current is limited by the series impedance RS. From this point on, the current follows the voltage as if the load were linear. The capacitor is charged by this current, and UCT increases with UT until UT reaches the top of the sine wave and starts to decrease again at a phase angle of 90 degrees. The diode bridge becomes reverse biased again, and the current IT stops flowing. The capacitor is no longer being charged, and the voltage UCT starts to decrease again as it discharges into the load R load. The procedure repeats for the negative half cycle of UT, but now with the rectified dotted part of UT. D1 and D2 work on the positive half of UT, and D3 and D4 on the negative half. The current IT has the same form as in the first half of the cycle, but now is negative. The current IT does not look like a sine wave, but more like an impulse signal. Harmonic distortion. Why is S squared no longer just P squared plus Q squared? We now can't just say S squared equals P squared plus Q squared, because we have to include Sn squared, the non-fundamental apparent power squared. So S squared equals P squared plus Q squared plus Sn squared. Continuing with the canal boat analogy, adding harmonics is like pulling the canal boat through choppy water. The waves cause a third force, perpendicular to the other two, which represents the non-fundamental apparent power. Harmonic distortion, a summary of calculations. This page summarizes the calculations of the E-device so far. You can check through the figures afterwards. We'll here just concentrate on the relationships: active, reactive, and apparent powers. The active power P is here the same as the fundamental active power, P1 equals S1 times cosine phi 1. That is because we define the harmonic voltage to be 0, so there is no harmonic contribution, pH, in this example. In general, P equals P1 plus pH, where pH is the average value of pHT. In this case, pH equals 0, so P equals P1. The corresponding fundamental reactive power, Q1 equals S1 times sine phi 1, is the largest reactive power component, and the only important one. The apparent power S supplied by the utility splits into the fundamental apparent power S1 and the non-fundamental apparent power Sn, which collects together all the harmonic powers: active, reactive, and harmonic currents. The unified method allows us to find the active, reactive, and non-fundamental currents and voltages, which IEEE 1459 does not define explicitly. Our example only shows the current components, as we assume the voltage to be purely sinusoidal. Note that while P and Q can be negative, so pushing power back into the mains, S is always positive. Harmonic distortion, performance parameters. Performance parameters represent the efficiency of the system. There are several different parameters depending on exactly what you want to measure in the circuit. The power factor is the total active power divided by the total apparent power, useful because it shows what the system is providing. The closer to 1, the more efficient is your system. Similarly, the fundamental power factor, often called the displacement power factor in the US, is the fundamental active power divided by the fundamental apparent power. Europeans here use cosine phi, which gives basically the same value, but it is sometimes easier to measure the individual power components. In most practical cases, only the fundamental component of the power does useful work. The non-fundamental active power will sometimes be useful in a heater, but otherwise not. The efficiency factor, defined in the unified method, is the useful, i.e., fundamental part of the real power, divided by everything you have to transport. The harmonic pollution is the non-fundamental apparent power divided by the fundamental apparent power. It is a quick estimate of the amount of harmonic pollution in the system. Smaller is better. Adding some numbers. Comparing power factor and fundamental power factor, or displacement power factor, shows the harmonic content. The power factor and efficiency factor are here the same, because there is here no harmonic voltage in our example, so no harmonic active power. While the power factor should ideally be 1, the harmonic pollution should be 0.